And so we're going to do lesson 24 in just a moment. But before we do, I want to remind us that we got this one last lesson here, and then new stuff on Tuesday, but this is the last lesson for the coming quest on Thursday, a week from today. And I just want to give us the highlights about that quest that's coming up a week from today. So roughly, the 3 topics that we have covered for this quest are factoring, and then solving quadratic equations. If you want to write this down someplace, you can. I don't know where it's going to go. And then graphing parabolas. So those are basically the 3 techniques that we've done most recently, and this is what's going to appear on the quest. And for factoring, we have 3 different kinds we've talked about. What are they and in what order? Greatest common factor, difference of 2 squares, and then the box method, right? Those are the 3 kinds of factorings. And so as an example of this, I gave you 4x squared minus 4x minus 48. So we look for greatest common factor first. What is the greatest common factor? It's 4, so we're going to pull a 4 outside. Take a moment to fill in those parentheses. Go ahead and write them down. Quest 4. Okay, what's left in the parentheses? Minus 12, right? 4 into that. Okay, so we have correctly factored out the greatest common factor, but that doesn't mean we're done. We need to factor completely, which means anything that shows up in new parentheses, you just have to spend a moment looking and asking yourself if you can do any more factoring. The thing in the parentheses, is it dots, difference of 2 squares? No, definitely not that pattern. Is it a box? I don't know, but it sure looks like the things that we do the box on. And so this one equals, I'm going to say dot, 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 box, just like we did before, but hiding the details. And it turns out if you use the box method here, you will get x minus 4 and x plus 3. Again, I'm not showing you like that 3 to 4 minute process on the side, but you do the whole box process and you get that other thing. And so that one is completely done, okay? So I show you that one to remind you that just because you have factored out the greatest common factor doesn't mean you're done with the problem. You still have to look at what's in the parentheses. Okay, solving quadratic equations. We had 3 techniques. One of them was using square roots. One of them was factoring. And the last one was the quadratic formula. And I'll show you an example of each of these 3 in just a second. So the square root technique is something like this. 4x squared plus 10 equals 17, something like that. What term that we normally have in our quadratic equations is missing in that purple equation? It's not that one. It's the b term, the thing with the x, right? There is no solitary x term. We've got an x squared, we got a constant, a couple of constants actually, but we do not have an x term. And if you are in the fortunate case where you have a quadratic equation with no x term, then if you just get the x squared by itself, then good things happen. So let's solve this one real quick. Subtract the 10 from both sides, so we get 7. And then solving for the x squared, I divide by 4. So that means that x squared equals 7 over 4. Right? And then what's the opposite of squaring something? The square rooting. And so I'm going to copy that equation just so that I have the opportunity to plop a square root on top of both sides. And when you do this square root of x squared, you just get plain old x. That was the point. And then over on the right-hand side, it's just 7 over 4. Not a whole lot you can do with that. Turns out you could bring the 4 outside because it's a perfect square. I didn't intend for that to happen. This is the answer, but you're going to lose a point or two if you do this. What did we forget? Plus or minus. So easy to forget. When you take the square root of both sides of an equation, you must put in plus or minus. I will share with you a theorem that I haven't shared before. If you are solving an equation, whatever the highest power is, that's how many answers the equation has. Say it again. Whatever the highest power of the equation is, that's how many answers the equation has. So how many answers is this equation supposed to have? It's supposed to have 2. If you just get me square root of 7 over 4, how many answers did you give me? 1. You missed 1. And if you look back at all of the equations we solved earlier this semester, like 3x minus 7 equals 8, how many solutions should it have? It should have 1, because that is the highest power. You add 7, you divide by 3, and you get your single solution. If we had that equation, which we will not solve cubic equations this semester, how many solutions does it have? It has 3. Right? So it's a nifty little check. Whatever that highest power is, that's how many solutions you have. Okay. All right, so that one's good. Factoring. Suppose that we do this one over here. Here's a factoring problem. 4x squared minus 4x minus 48 equals 0. Does that left-hand side look familiar? See it on the board? It's this factoring problem I gave you up here. What's the difference between this green thing and that red thing? That one's an equation. The other one is just an expression. They are fundamentally different creatures. The solutions are going to be similar, but they are fundamentally different, and the answers at the end of the day are fundamentally different. The technique here is to factor, and so we've already done it. I'm just going to copy the final factored version over here. We'll say, dot, 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 same stuff that we did over there. 4, x minus 4, x plus 3 equals what? 0, right? It was equal to 0 before. It's still equal to 0. In the green factoring question, we were done once we had factored, but here we are not done until we get x equals some number. And so this is the part where we just say, hey, we need to split this up into different equations. Either x minus 4 equals 0 or x plus 3 equals 0, right? One of those two things in the parentheses must be 0. If you are a completionist, there's actually a third thing you can put equal to 0. What is it in this case? 4, right? I actually have 3 things multiplied together. It's not just the 2 parentheses. There's also a times 4 in the front. And so technically, one of these 3 things is going to equal 0. It's not 4, because 4 is not equal to 0. So like you can write it, and then you can ignore it. And then you find the actual solutions from the, see, I'm hip, I'm cool, I'm with it. Right? Yeah. Anybody who says I'm hip is definitely not. All right, so then we solve our equation here. X equals 4, x equals negative 3. Okay, so take a look at the difference here. In green, the final answer was that factored thing. In red, the final answer is x equals 4 and x equals negative 3. On the quest, I'm going to give you a whole page of problems that says factor these. They are not equations. They cannot be solved. Are your final answers going to look like green or red? When I say factor these, they're going to look green. Do not give me red. I'm looking for green, okay? Factor is not supposed to look like x equals 7 at the end of the problem. And then I'll give you another page of equations, and I'm going to say solve these, and then you better give me stuff that looks like red. But you got to know the fundamental difference between those two, right? One's an equation, one is just an expression. Okay. The other technique for solving quadratic equations was the quadratic formula. And so these are ones like you just did in the activity here. You just use a quadratic formula over and over again. And so, you know, x equals negative b plus or minus dot, dot, dot. I'm not going to go any farther with that one. You just did a bunch of them in the activity. But I want to be really clear about my expectations for this coming quest. The fact is, this square rooting idea that we did in purple only applies to a very limited class of quadratic equations. What did we say was the telltale sign that says we could do this? What was missing in that original equation is the x term. So if you have no x term, do that. But if you've got an x term, that technique is not in play, right? Okay, what made this red factoring version work? What made it work is that I intentionally picked this thing to be factorable. And so if I give you a quadratic equation and it happens that you can factor it, then you are welcome to do this factoring technique. But these numbers were specifically chosen so that everything would work out. Whereas in the activity problems that you just did, you couldn't factor those ones. Anything that still had a square root left in the answer means it was not factorable in the beginning. And so here's the deal. The quadratic formula will solve any quadratic equation under the sun. It will solve the ones that you did in the activity where they were kind of messy and you couldn't solve them with any other technique. It will solve this red one even though it factors. You could use the quadratic formula instead of factoring. It will solve the purple one even though you could do this square root idea. Quadratic formula will get you the right answer every time. So of the three techniques up there in red, which is the most powerful equation solving technique? Quadratic formula. And so some people get in their heads, oh, I can forget about the square rooting and I can forget about the factoring technique because the quadratic formula solves everything. And it does, but you can't, because I'm going to give you a page that says solve these equations using any technique you want except for the quadratic formula, which means you have only the other two options, factoring or square roots. I'm just being clear about my expectations right now. I know the quadratic formula can solve everything under the sun, but there are other techniques, and sometimes those other techniques are they're just easier. But quadratic formula can be a big old mess. I will also give you a separate equation that says solve this one with the quadratic formula. It will look just like the ones in the activity, give me a simplified radical, and also give me a decimal. It'll be just like the ones you did today, right? So even though the quadratic formula can solve any equation I throw at you at this next quest, you can't just use it on every single problem. Okay, the directions will say all of this, but I just want to make sure that you understand what we're looking for. Okay, so I think that's about it in terms of factoring and solving quadratic equations. The other thing is graphing parabolas. It's pretty straightforward. I'm going to give you an equation, y equals something with an x squared, and I'll say graph the parabola, and you'll go through the process just like we did the other day. You don't need to worry too much about like memorizing the process. Remember, it was like, does it open up or down? Find the y-intercept, find the x-intercepts, find the vertex, find the symmetric point, and then connect them all, right? Like we had this process. You don't need to write that all down on your reference sheet. And again, you can make a reference sheet and bring it for that quest. And you don't need to memorize it because on the quest, it will say, like, it'll just be parts A, B, C, and D. Does it open up or down and Y? And then you fill in the blank. What is the x-intercept? And then you fill in the blank. What is the y-intercept? And you fill in the blank. So I'll lead you through the process. All right, I think that's about all I had to say about the quest. I know normally we don't do this kind of thing like before each quest or each test, but in this case, because we had the three different kinds of factorings and because we had the three different kinds of ways to solve the quadratic equations, and because I'm limiting you to not use the quadratic formula on every problem, I just wanted to take 15 minutes here to make sure that we were clear on what to expect. Any questions on any of that? Okay. All right, so let's go back here. So I think we're here on 192. Do we have that right? 197. 197. Okay, our daily summary. In this lesson, we see how we can use part of the quadratic formula to determine the nature of the roots of a quadratic equation. We will define that word nature soon. And we discover a brand new set of numbers called the complex numbers. You may have seen those before in some other course. We have not talked about the complex numbers in this course, but if you've seen I, the letter I in a math class, that was part of the complex numbers day. Okay, so we're going to just skip some of this stuff because I took kind of a long time talking about the quest. Let's just solve this. Let's solve this equation right here. So we'll do the quadratic formula on that. And we're going to try to do this a little bit quicker now because you guys are experts at the quadratic formula after all the practice we've had. So the first thing is a negative b. What is negative b in this case? 4, right? Plus or minus b squared. How much is b squared? It's minus 4 squared. That's a positive 16. Minus 4ac, minus 4 times a times c. 4 times 1 times 5. 4 times 1 times 5 is 20. Divided by 2a, that's just 2. Like I said, I'm doing this one quicker. I know you can do it in your own time, at your own pace. And let's do the next simplifying step, 4 plus or minus square root of negative 4 divided by 2. So what is our problem? Nick. Can't do the square root of a negative number, right? There's no way, right? I mean, like maybe you think, oh, square root of negative 4 is 2. Well, that isn't right because how much is 2 squared? 4, which is not that number in there. And then you say, oh, okay, well, maybe the answer is negative 2. But that isn't right because how much is negative 2, the whole thing squared? It's still 4. And so because anytime you square a number, you get something positive, it seems like we are done. We're toast here. We can't do anything further because you can't take the square root of a negative. Okay. Just because you can't do something doesn't mean mathematicians are going to get stopped by that. We're just going to invent something that allows us to proceed. So here we go. Number 2, what do we do with the square root of negative 4? We know that simplifying the square root of a negative number is not a real number, but can we give meaning to the square root of a negative number? And the answer is yes. Mathematicians have created a number system called the complex number system. And these complex numbers allow us to work with the square root of a negative number. I know that I use the word imaginary, and if you, well, I'm using it now, so the letter I for the imaginary number. The word imaginary is a very poor choice. It somehow makes imaginary numbers seem less legitimate than the real numbers that we all know and love. But these numbers that we're going to introduce, even though they are sometimes called imaginary numbers, that's not supposed to be like a judgment on them. It's just a word that we're stuck with here. But they are perfectly good numbers, just like all of the numbers we've been working with all semester. Turns out complex numbers, these new ones we're about to play with, are used in many fields such as engineering to find quantities involved in electricity and in medicine to calculate flow of blood in the bloodstream. So even though they are called imaginary, doesn't mean they have no actual applications to real life. They have plenty. Okay, so before we get to the square root of negative 4, which is the one we're stuck on, let's think about the square root of negative 1. Turns out that the question of how to define that square root of negative 1 arose back in the 16th century when some Italian mathematicians were trying to solve cubic equations. Riley asked us about an x cubed equation earlier today. So way back when, they were trying to solve these kinds of equations. How many solutions were they looking for? 3 is right. Their efforts led to the invention of a new class of numbers, beginning with this definition. We denote the positive square root of negative 1 with the letter I, that is, excuse me, thank you. That is, I is the square root of negative 1. It is a brand new definition. If you see the square root of negative 1, you get to just replace it with the letter I. We haven't done anything magical. We have just redefined that symbol, the square root of negative 1, to be I. It is not so uncommon in math for a famous number, an important number, to get symbolized with a letter. What's the most famous number that you know of that we actually call a letter? X is typically a variable. I'm looking for a particular number, but we refer to it with a letter. What is it? What letter? Pi. If I say pi, you have no problems with the fact that that's a letter. You have an association in your mind. So, oh, pi has something to do with circles, and pi is approximately 3.14. It's a famous enough number. We've just decided to call it a letter, pi, Greek letter in that case. In that case, some of you might have seen the number e. It's okay if you never have. If you continue to take college algebra next semester, you will see the number e, and you'll play around with it a bunch. It's around 2.718. But again, a famous number. We're just going to call it a letter. Square root of -1, a famous number. We're just going to call it a letter. So here's how we find the square root of any negative number using our product rule about square roots from pretty recently. If you see the square root of -4, you can say, okay, -4 is really -1 times 4, yes. And then square roots work really nicely over multiplication. We know we can split into two different square roots. We have just defined this thing right here. You see square root of -1, you changed it to what? I. It's just a definition. No tricks, no funny business. And then oftentimes that's the end of the game, but if you can simplify the square root, you should. Square root of 4 is just plain 2. And typically you put the number in the front and the I in the back if it's a nice number like this. The next example is the square root of -49. Same idea. -1 goes in the front. -1 inside square root becomes I. Square root of 49 is 7. So the square root of -49 is just 7i. All right. I'm going to make up another one that isn't here right now. Let's suppose that we do the square root of -21. So that's really -1 times what number? 21, right? Just plain 21. And then we split. And then that square root becomes what? I. Can you do anything to simplify the square root of 21? Nope, so we're done. I don't want to give the impression that every time we have i's, it's just like a nice whole number out in the front. It's not always the case. Okay, I square root of 21, that's it. And so actually, if we look at the beginning and the end, maybe we have a shortcut. If you see a negative inside of a square root, what ends up in the front of the square root is an I, and then the number inside becomes positive. That's it. That's all we do. And so for example, if I see the square root of -12, what am I putting in front? I, and then square root of positive 12. That's it. I don't need you to go through the details that we did where you peel off that -1. If you can go further with the square root, you still have to. That hasn't changed. What nice number goes into 12? 4 goes into 12. And so you can see I've written 12 as 4 times 3. 4 comes out as what number? 2. And so that 2 is right there. And typically, this is the order in which you write things, but it doesn't much matter what order you put them. Okay, if you have a number of the form a plus bi, that's called a complex number. So for example, 3 plus 2i, or 4 minus I square root of 21. These are complex numbers. Complex because they're just a little bit more complex than the real numbers that we've seen, right? Like we recognize, you know, like the real numbers are part of these things, but these are just more complex. Okay, I think we are good. All right, so then that gets us in a position to finish the problem that we had up above. So first verify that this is where we left off with that example we were working on. Is that right? Okay, and so then we go farther with this thing right here. So we'll just read that -4. That negative comes outside as, or what are we putting in front of the radical? It's an I. There it is. And what does that -4 become in the radical? Positive form. And so that's there. But then if you can go farther, you must. And the square root of 4 becomes just plain old 2. So there's a 2i there. And then just like you did today, we know we can split into two fractions, right? Both get the right denominator. And then 4 over 2 reduces, and the 2 and the 2 cancel. And so we just get 2 plus or minus I. 2 plus or minus I. Okay. So let's take a look at here. First, a quick definition. A rational number is one that can be written as a ratio of two integers. For example, a half. Ratio just means divide. And you can see the word ratio in the beginning of rational. So rational number is one that can be written as a ratio of integers. And if you have a number that still has a radical in it that can't be simplified, that is called an irrational number. If you wrote that as a decimal, it would be like 3 point, and then it would go on forever with no patterns and never ending, right? Okay, let's take a look at the graphs. Again, the quality of my graphs up here is not so great, but I think on your page it's better. So I'm looking for x-intercepts here. How many x-intercepts do you see? 2. And it sure looks like those are nice numbers, 1 and -6. Nice numbers, we really should be calling them rational numbers. 1 and -6, you can think of both of them as just being simple old fractions, rationals. Okay, so in this case, 2 rational solutions is what we have. Take a look at the next picture. How many x-intercepts here? Just a single one, right? Over there we had 2 x-intercepts, but here we have only 1. And rational or irrational, that number there. It sure looks rational. It looks like it's plain old 2. In this case, 1 rational solution. Coming down here to graph C, how many x-intercepts? 2. Okay, now there's absolutely no way for us to look at this and know whether those are nice numbers or not nice numbers. But we actually studied this particular graph last class, and the solutions that we came up with were something like, I don't know, 1.449, and then it went on and on and on the calculator. Rational or irrational? Irrational. These are not nice numbers. We had a square root still left in them. So our conclusion here is we have 2 irrational solutions. And then the kind of funky one, how many x-intercepts? None. None. Well, what kind of solutions would give you no picture? Well, I mean, I know that every quadratic equation has how many solutions? 2. We said the highest power. Every quadratic equation has 2 solutions. If I cannot see those solutions as x-intercepts, what kinds of numbers must these 2 solutions have been? They must have been imaginary numbers. They must have been complex numbers. They must have involved i's, because if they were just plain old real numbers, I'd have seen them hitting the x-axis. And so if you have no x-intercepts at all, you got these 2 complex or imaginary numbers. Okay, so that's the sort of graphical. Now we're going to connect the graphical to the equations. We've got all these quadratic equations here. Turns out that these equations are exactly the ones that are graphed up above. It's not a 0 equals, but it's a y equals for each of those parabolas. But I'm interested in the x-intercepts. So I'm just going to look at the 0 equals. Okay, we're going to define a brand new word here. It is called the discriminant. And the discriminant for our standard ax squared plus bx plus c equals 0. The discriminant is b squared minus 4ac. Where have you seen exactly those letters, b squared minus 4ac? Where are they? They're in the radical in the quadratic formula. Not a coincidence. We're going to see why we care about the thing that's in the radical in the quadratic formula. Okay, let's run through here. So we're going to calculate b squared minus 4ac for these examples right here. How much is b in this case? 5. So this is a 5 squared minus 4 times, how much is a? 1 times -6, right? So it's like doing just part of the quadratic formula. Okay, so we go 25 there. Minus minus makes a plus for me. 24 there. 49 is the discriminant, just a single number. I'm going to split the rest of these discriminants up real quick just to save us time. These 2 tables are doing B. These 2 tables are doing C. These 2 tables are doing D. Just do the one discriminant and shout out an answer when your table agrees. All right, so go ahead and just copy the other answers there. You can do the calculations later if you want to, but let's save a little bit of time and move on here. And what I want us to do now is just copy the natures that were typed below each of the graphs. For graph A, it said right below the graph, it said 2 rational solutions. What does it say for B? 1 rational solution. Just put that there for B. This is just copied from the graphs up above. We're going to fill in the rest of this table and then make some connections between the number and the words. For part C, was 2, what kind? Irrational, 2 irrationals. And then finally, part D was 2 imaginary or complex. All right, 2 complex. Okay, check this out. If you wanted to solve this equation using the full-blown quadratic formula, you'd have to do this b squared minus 4ac anyway, and it would be sitting inside of that square root, right? So imagine that you had the whole quadratic formula with all the other stuff, and then the square root of 49. Is that square root of 49 something nice or not so nice? It's quite nice. It's just plain old 7. And so you're just imagining, like -5 plus or minus plain old 7 divided by 2, something like that. And what kinds of numbers are we going to get there? Well, if the answer still has a square root in it, then it's irrational. But that square root disappeared because 49 is really nice. And so it's going to be rational. And how many solutions are we going to get? Well, there's a plus or minus, right? So we get one solution when we type in the plus, and we get a completely different solution when we type in the minus. So 2 rational solutions makes total sense. What is special about that 49 that led to this conclusion? Yes, it became 7. So what kinds of numbers there will have this conclusion? Perfect squares. That's the key, right? That's what made 49 work. If it were 50, it would be different, right? If it were 50, you would still have a square root in your answer. But if it's a perfect square, it all disappears. The conclusions that we're making are all summarized on the next page. So right now we're just kind of understanding. You don't need to frantically copy the words that we're using here. Okay, 0. So again, imagine. Square root. What is the square root of 0? It is 0. And so I'm just going to make up some numbers. Maybe it's like -5 plus or minus square root of 0 over 2, something like that, right? And so it's -5 plus or minus 0 over 2. How much is -5 plus 0? -5. How much is -5 minus 0? Is also -5. So then would you guys agree that the 0 plays absolutely no role? How many answers did we get? 1. The only reason we got 1 is that we had a 0 sitting over there. That's the only time you will ever get 1. If you look at the rest of these, 2, 2, and 2, the only way to get a single solution is if you get a 0 there, because otherwise you will have a plus and a minus, and they will give you different outcomes, okay? All right, this technically contradicts something I told you earlier today, which isn't really part of our curriculum, but how many solutions does every quadratic equation have? 2. But here's a quadratic equation. Then how many solutions does it have? It has 1. I don't like to lie to my students, but occasionally I have to. But I will say that if you do the box method and you factor this guy, you will get this, x minus 2, x minus 2. Okay, that's using the box. And so that means that you write your equations, right? Either 0 equals x minus 2, or what's the other equation? 0 equals this other guy, which happens to be the same guy, but I'm just naively writing down on my process. And how much is x here? 2. And how much is x here? 2. Okay. How many solutions does it have? It technically has 2. They were both the same exact number, but that's not my fault. I mean, there were 2 different things that gave me the same number. So as long as you allow us to count repeats, then the thing I said about the power was true. The power is the number of solutions, but you got to let me count repeats. Okay, so don't worry about that. Just technical details there. Let's come to this guy. That 24, again, appearing inside of a square root. Is the square root of 24 rational or irrational? It is irrational. Technically, you can still simplify it. What nice number goes in? It's 4, right? 4 times 6. But even though the 4 is going to come out of the square root, the 6 will still be in. So there's no getting around the fact that there will still be a square root in your answer. And so you're going to get irrational numbers, and you bet we're going to get 2 plus or minus. And then the last one was the square root of -4. What kind of number is the square root of -4? It's one of our complex or imaginary numbers. And so, of course, it's going to be. So what kind of number here is going to give you the complex numbers? Anything negative. Anything negative. So here's our big summary. This was good because it was a perfect square. This was just plain 0. It's got its own separate case. This one is any positive number that isn't a perfect square. So 20, 21, 22, 23, 24. Jump up here for 25 for just a second. 26, 27, 28, 29, 30, right? Any positive number, perfect square is rare. Most of them are going to be that flavor. And then anything negative has 2 complex solutions. So all of that is written here in this A, B, C, and D. I'll just read C, and you can read the rest of them later. If b squared minus 4ac is positive and is a perfect square, then there are going to be two rational solutions. That's what's written in the on the previous page. So we got our four cases. Let's jump to the activity here. I know the activity is usually you guys on your own. Let's just do one of these together, just so we can see what they look like. Okay, we are going to do number 4 together. Let's take a look at 4. Is this in a form where I'm ready to figure out what A, B, and C are? No. What number do we need? Got to have a 0, right? So 3x squared minus 2x. And then we bring that negative 8 over by adding 8. So plus 8 equals 0. Okay, so let's do our discriminant. You don't need to write this step for me, but if it helps you, write out the values of A, B, and C. Okay, so let's do our discriminant calculation right here. So the formula for the discriminant is b squared minus 4ac. Negative 2 squared minus 4 times 3 times 8. No square root, just the stuff inside. That's our definition for the discriminant. Did I do something wrong here?
Oh, right.
I'm just did anybody see a mistake here? Because I'm looking at my key and looking ahead a step. My key is not agreeing with what I think. Oh, I gotcha. I was looking at the key for the even more practice and not for the activity. Okay, we're good. Okay, so we do our calculation here. This is 4 minus 4 times 3 times 8. 12 times 8, that's 96. Good. So negative 92. What is that called for this quadratic equation? That is the, so the D discriminant. That's our new word. That is the discriminant. You just have to pick which of the 4 cases you are in. I'm asking you for the nature of the solutions. It's just 4 cases. It's either positive and a perfect square, positive and not a perfect square, 0, or negative. Which one is this? This is negative. And the conclusion, anytime the discriminant is negative, is always the same. How many solutions do we have? 2. And what kind are they? They are complex. And that's all we write. 2 complex. And so it's kind of cool to know ahead of time, like we haven't done the full-fledged quadratic formula, but we know for sure that if we did the full-fledged quadratic formula, we would end up with 2 solutions and they would be complex numbers. And now let's verify that by actually finishing. This says find the solutions. So we'll do our negative b. How much is negative b? Well, I'll write the quadratic formula here. Okay, so negative b becomes 2 plus or minus square root of. Now we've done all the work. Just put the single number final answer in that radical. What is it? It's negative 92. Don't do it again. B squared minus 4ac. It's negative 92 after all the calculations are done. Divided by 2a, how much is that? 6, right? 2 times 3. Okay, so I'm going to put dot, dot, dot here. I want to say that doing that discriminant, it's not really any more work. If you have to do the whole quadratic formula anyway, you're going to do the b squared minus 4ac along the way. So it's no more work. Just gives us a nice little shortcut, like a quickie way to find what kinds of solutions we have. And so, yeah, so I think that's it. And then you'd have to simplify this just like we did with all the ones today, although this one will have what letter popping out? I, right? That's the brand new thing. Okay, so I didn't give you time to do the activities here. Technically, the homework for this one, according to the calendar, is going to be due Tuesday. I'm willing to push that off. I mean, if you can do it for Tuesday, that's fine. But I'll plan on spending like the first 10 minutes on Tuesday just letting folks practice a little bit here.
What lessons are homework?
So technically, just the first one today is the one that's due, which was lesson 20. Which one is it? 24, no, 23 is the one we finished today. So just 23 technically. But if you can do this too, that'd be great.